So now we're going to discuss sequences, and in particular numerical sequences. In this course, we will be mainly interested in sequences of real numbers. So here are some examples of sequences that we are familiar with. So of course, the first sequence that we ever encounter in our life is this arithmetic sequence, or the sequence of natural numbers that we learn when we learn how to count. And of course, another very famous type of sequences is the geometric sequence, where every factor is multiplication of the previous one by some constant factor. So here, every time the next element is the double of the previous one, and here we add one. So we have this geometric sequence, and of course we can form more complicated sequences. For example, we can take those two sequences and mix them together and intertwine them. So this sequence, the elements of this sequence are going to be here on odd places, and the elements of this sequence are going to be on the even places. So we get this mixed sequence, right? And often, in some logical puzzles, we're being asked to guess the next element in the sequence. So for this particular sequence, we see that we constantly add 2, so this is an arithmetic sequence, and our most natural guess would be, or the first guess would be, that the next element should be 8. But as we will see, specifying an infinite sequence, or potentially infinite sequence, by only finitely many elements is impossible, and so this sequence it is not well defined in general. So each such specification of finitely many elements, when we have finitely many elements of a given sequence, there are actually infinitely many ways to complete this sequence. But still, we think that there is some rule for generating the next elements from the previous ones, right? And so this will lead us to the definition of how should we define a sequence as something logical, right? And of course, we will be interested in sequences of real numbers, and only infinite sequences will be of interest. And so one attempt to define a sequence, as I was saying, is that to say that a sequence is formed when we have some logical rule to generate the next element from the previous ones, or to generate all the elements in the sequence. As for example, in this sequence, we start with 2, and then the next element is obtained from the previous one by adding 2, or we could write some formula, right? Okay, so this rule of assignment is almost accurate, right? We know a term in mathematics that is that we use for rule of assignment, but to say that there is some logical rule is not rigorous enough to define it, as a mathematical definition. So saying this just abstract rule or logical rule is not a good enough of a definition, but we have something very close to rule of assignment, and this is the notion of function. So if you want to define a sequence, so a rigorous definition of a sequence would be that a sequence is actually a function that assigns to every natural number a real number. This would be a real sequence, right? A sequence of real numbers. So, and when we say function, this becomes very rigorous, and this intuitive notion of rule of assignment is underlined, right? So to any element of the natural number, to each natural number, we assign a real number. And so we denote by an the value of this a function at the natural number n. And this an is called the nth element of the sequence. And we think of a sequence as this ordered collection, an infinite collection of numbers, real numbers in this case, a1 up to an, and it goes indefinitely. So this ordered infinite collection that is obtained in this way by listing all the values of this given function is a sequence, and this is how we denote it. Now, it somewhat reminds us, curly brackets reminds us a notation of set, but just a word of caution here, because in set, the only thing that matters in sets is just the elements, and not the order. So two sets can be considered equal if they have the same elements, but listed in different orders. Here, the order matters, so it's this, so to say, ordered collection. We have to keep this in mind, okay? And in general, now we see that with this definition, as we defined a sequence to be a function from natural numbers to the real numbers, we see that in order to define a sequence, all we need is just a function from natural numbers to some set. All we really need is that for this function to be defined, and then any rule of assignment that assigns to a natural number an element of another set is a sequence. So we have a very general way of defining sequences. And so we could have sequences of natural numbers, rational numbers, real numbers, integer numbers. We could have a sequence of complex numbers. We can have a sequence of points in plane. We can have sequence of points in some abstract n-dimensional space. We could have sequences of sets, and we can have sequences of functions, right? So it's a very general term. Okay, so here are some ways in which we can define a sequence. We need to define this function. So one way is to give an explicit formula. So remember that we said that this a is a function. So here is how we specify it. We give for each n how we compute the value of the function for this n. So this is explicit formula. So that's a way of specifying a sequence, and this is the direct and most common way to specify a sequence. But there are ways to specify a sequence, for example, by this algorithm, right? So we could say that an is the nth digit in, for example, the decimal expansion of pi. So the first element would be a1 would be 3, and then a2 would be 1, etc. And so this sequence has very complicated behavior, and we're not specifying all the sequence, and as far as it is known, and today it's an open question, there is no formula to generate all the numbers. So someone who would want to find the nth element would have to compute it. There is no like simple formula which we can plug in and get those numbers. Okay, and there's also this famous Fibonacci sequence wherein we define the sequence by an algorithm again. So we say that the first element is 1 and the second element is also 1, and then for every n that is greater than 2, we can compute the next element from its two predecessors. And this is the rule for computation. So of course we can use this rule to compute that a3 is 2, and then that a4 is 2 plus 1, which is 3, etc. And it is somewhat surprising, but a general formula in this case can be found, although it was specified algorithmically in terms that we need to compute this. This general formula can be proved that this general formula gives the nth element. So this is the golden ratio, right? What does it do here? How does this appear here? And this is called the negative golden ratio. And these are irrational numbers, and all those are supposed to be integers. And in fact, this formula gives all integer numbers, but this is a discussion for another lecture. Okay, so how would we visualize a sequence if we want to see it visually? Currently, it's something abstract. So of course, we have this way to think of this as a function. And it's a natural way, there is a natural way that we will see to think of this function, of this sequence, as a sampling of a function, or of a continuous function, or a function which is given by a formula, which we will see. And it's a very important and useful way of thinking in signal processing. When we have some signal, for example, the signal of my speech, which I'm talking, is being converted to a digital sequence of numbers which is stored on the computer, and which the computer can decode and reproduce the sound. But of course, it's not a continuous sequence. It's a sequence that was sampled by the microphone at discrete elements of time of this continuous signal of my speech. Okay, and so if we're thinking about it this way, so if we have a function that is defined on the natural numbers into the real numbers, then to each n corresponds this an, and we can plot this by a collection of points, which we'll shortly see how. And in addition, we will often, to visualize a sequence, we will think of it as a sequence that lies or on the x-axis or on the y-axis, and then we would plot those points to see the sequence. So let us now see a visual way of seeing a sequence and its elements. So let us now see how can we visualize this sequence using this Desmos, which is a free tool and very convenient, very powerful tool. So first we create a list of here 10,000 elements, because Desmos has this 10,000 elements list limitation. We cannot have a list with more than 10,000 elements. And so that's the way that we write that n obtains values from 1 up to 10,000 in skips of 1. This is the specification of list, and then we can write the formula for our sequence. This is the sequence from the slides, which we have seen, and we will visualize the sequence. So now if I click here, Desmos would plot the first 10,000 elements of the sequence, and we see the sequence, as we think of it, as a correspondence to each natural number to one that corresponds to this value when we plug in 1 into this formula, and when we plug in 2, we have this value that corresponds in this formula, etc. And so, as I mentioned, we can think of this sequence as being a sampled function. Like there is a way, right? There is almost when we look at this, we almost want to, connect the dots in some function or some way to extrapolate it. And there are infinitely many ways to extrapolate, but we can find a natural function. There are infinitely many such functions that would extrapolate this continuously. It's not our subject, but if we want to think of this sequence as a sampling of some function, then we can look at this function. So f of x is this, and the idea is that for natural numbers, the sequence and the function in values, they coincide, and for not natural values, this function is defined where the sequence is not defined. And the idea is to use the property of the cosine function that cosine of n pi is actually minus 1 to the power of n. And so if we plot this function, we see that these points are kind of sampling of the function. Similarly, if we have a continuous signal, for example, a signal of speech where I speak and it's varying pressure of air, and it is sampled, this pressure is sampled at some constant time intervals, and then we see this sequence of numbers which will be stored in the computer and turned into then again an analog signal, right? So in this way, the way we obtain this sequence, it's actually a sequence, it's a visualization, it's a one way and a convenient way to visualize a sequence on a plane, but this is also a sequence of points in the plane. So it's sequence in R2. So there is two ways to think of a sequence. We can think of it, of course, we're interested only in the values an, but the way we visualize this, here we obtained a sequence in R2, for example. And often we will use it, so we want to think of it as a function, as a sequence that lies on one of the axes. So we can take the sequence and project it to the y-axis, and this way we have one-dimensional sequence, only sequence of real numbers. And in this case, we think of this sequence when we, if we do not show this, then this is a sequence that lie one-dimensional of real numbers that lies on the y-axis, and similarly we can think of this sequence as lying on the x-axis, and this would be the visualization of the sequence. And so let me plot it this way. For this video, it will be convenient when we want to define the notion of a limit. So it's convenient to think of it this way because, as we can see, if we zoom out a little bit, it's going to be harder and harder to see, but this sequence approaches some value. And the farther we go, the closer it seems to be to this value of 0.6. We'll prove that this is actually the limit. And the farther we go, we see that the closer the element of the sequence are becoming to this limit. So we'll have to define this rigorously. But this will be the main focus of this lecture, to rigorously define what it means for a sequence to have limit and what it means to converge. So we see that the farther we go, the closer the elements of the sequence become to its limit. So it's something that we'll have to prove, that 0.6 is actually the limit of the sequence. So let us go back again to define rigorously what the notion of limit means. So as we said, we would be interested to see what it means for a sequence to tend to some value or to converge to some limit, as we've seen with the visualized sequence that it approaches to the value 0.6, and we would like to see what it means and how to rigorously define this. So let's see a few examples. So for example, this sequence would tend to 0 or converge to 0. And the reason for this, I mean, we can see intuitively what happens. The bigger the value of n, the smaller 1 over n would be. And so we can make those elements of the sequence to be as close to 0 as we only please in terms of value. So for example, if we take n to be 1000, then starting from n equals 1000 and on, the value of all the elements that are distance between the elements of the sequence and 0 will be less than 1000. And if we take n to be 1 million, then starting from 1 million and on, the distance of all the elements in the sequence from 0 from that point on will be less than 1 millionth. And we can make it arbitrarily close if we want the difference or the distance of the elements of the sequence from the limit to be less than 1 billionth. Then starting from 1 billion, in this case it's easy to see, the distance between the elements of the sequence and 0 will be less than 1 billionth. And we can do it for every positive number that we pick to be like the closeness threshold, right? So the really thing that we need to define here is what it means to be close and how do we measure the distance, right? And we see that if we take n big enough, the farther we go, the closer the elements of the sequence become to the limit, and then we would like to make this notion precise, okay? So, right, so how do we measure distances? Well, on the real line, there is a natural way to measure distances. And basically, for two numbers x and y, we would like to say, okay, the distance between x and y is y minus x or x minus y, whichever is the positive one. If y is greater than x, then the distance between y and x is y minus x. And if x is greater than y, then the distance is x minus y. And so for this, we have the absolute value function. And the distance that we have defined intuitively is defined by this distance function. So we see, once again, that we need this notion of distance. And here we have defined actually a function of two values, right? This function takes two real numbers and returns a number, which is the distance of these two elements. And this is a very important concept in mathematics, this distance function, which is called a metric. So let us talk a little bit more about this distance, because the notion of distance is the only thing that we really need to define the notion of closeness and the notion of a limit. So let's talk a little bit about those distance functions, which are called metric and have very crucial importance in mathematics and in topology. So what we have done here, we have defined a function that takes two real numbers, a pair of real numbers, and assigns a third real number to them, which is positive, and it's in fact the distance between x and y. Okay, so what are the key properties of this distance function? Well, property number one is that it's clearly non-negative because, you know, it's the absolute value. And we expect that the distance between any two entities between which the distance is defined would be a non-negative, and of course we want the distance to be zero unless only in the case where these two distant entities are the same. So of course, in case of points on the real line, we want the distance between them to be zero, if and only if it's the same point, right? So this property of the distance function, that any distance function is desired to have, is called positivity. Another property, it's just a property of the absolute value, that it turns out that this function is symmetric. And in our, at least intuitive understanding, it is natural to have that the distance, at least walking distance between two points, would be symmetric, right? But for example, it's not necessarily for driving distance when you have one-way streets, right? So if you go from point A to point B, you drive it on a car. If you have one-way streets, that it's not necessarily that you can travel the same road back or backwards on the same road. Maybe you'll have to take a longer pass on your way back, right? So it's not so obvious, but here it's an obvious property, and this is something that we want every distance function to have. And the third property, which we'll yet need to prove, is the really non-trivial property, is called the triangle inequality. And some of you may be asking yourself, where is the triangle here, right? And how is this related? So, in fact, this is the only non-trivial property of the distance function, but it's really desired and has crucial, important consequences. So, let us talk a little bit about this triangle inequality in this context. So, the triangle inequality is actually an inequality from Euclidean geometry in the plane. So, suppose now that x, y, and z are not necessarily real numbers, but just points in the plane, right? And dxz is the distance between x and z, and the yz is the distance between y and z, and the xy is the distance between those points x and y. Suppose that we have some function that measures the distances. So now in Euclidean geometry, the triangle inequality says that for every triangle, the sum of any two sides is bigger than the other side. And so if we translate this to the distance function, and we want this distance function to satisfy this intuitive property that, or our intuition from Euclidean geometry, then we need to demand, for example, for this distance, that the length of this side in this triangle is the xy. And so we would demand, right, the triangle inequality would apply that the distance between x and y is less than the distance from x to z and plus the distance from z to y, right? This is the triangle inequality translated to the metric. Okay, but here I have another theorem. It's actually a property of the absolute value function, and I say that it's called the triangle inequality, or inequality for the absolute value function. And so you would be right to ask again, where is the triangle here? And we will see the answer to this shortly. And we'll see how this inequality implies the triangle inequality for the distance functions we have defined. But first, let us prove this really important inequality. Typically, this part is the famous one, and this one is less famous, but it's also very important and very convenient. So we'll prove both sides. Okay, so let us start with the proof. Okay, so for any two real numbers, we have this, right? X is between the absolute value of x and the minus absolute value of x. In fact, x equals to one of the values. If x is positive, then x equals to the absolute value of x. And if x is negative, then x equals the minus absolute value of x. So, but clearly this inequality holds for every x. It is between the absolute value of x and minus absolute value of x, and similarly for y. Now, let's add those inequalities. So what do we get? What we get once we add those inequalities, we have that x plus y for every x and y has to be less than this and more than this. So by the definition of the absolute value, it means that the absolute value of x and y is no bigger than this. So we've proved the first part. Now let's prove the second part. Okay, so now we will use this nice trick, which will be very convenient in other applications, so bear this in mind. So we'll write x as x plus y and minus y. So of course the absolute value of x equals to that, to this. And now we use the first part of the triangle inequality. So we will say that this is no more than x plus y plus the absolute value of y. And now we can switch the absolute value of y to the other side, and we have that the x plus y absolute value is bigger than that. But x and y are absolutely arbitrary numbers, and there is absolute symmetry in the values of x and y, so just interchanging their roles by the same procedure, we can conclude that the absolute value of y minus x also has to be smaller than this. And again, this means by the definition of the absolute value, it means that the absolute value of this expression, whether it's x absolute value minus y or y absolute value minus x, it has to be no bigger than this. So we have proved the second part. Now we have this important corollary that in fact, if we look at this distance function that we have defined, then it satisfies this triangle inequality. And now it's using this inequality, triangle inequality that I called, that we've proved, that previously called the triangle inequality for the absolute value. Now using this inequality that we've proved, it will be for this function a straightforward demonstration. So let's see how it's done. So we start for this function, distance function that we have defined. The distance between x and y is x minus y, and a very nice trick that is also often used and will be often used in this course. We just interject another value here, so we'll have x minus z and plus z minus y. So again, we change nothing because this z cancels here. And now we use the triangle inequality that we've proved to separate the two, and we say that the absolute value of this is no more than the absolute value of x minus z plus z minus y. And again, by definition, this is the distance between x and z, and this is the distance between z and y. And so we have shown that for this distance function we have defined that it satisfies the triangle inequality. So this is very, very important. And so any function that will satisfy those three key properties will be called a metric. And so if we have an arbitrary set on which we have a way of measuring distances, and we measure the distance with this some function that says the distance, but our demands from this function is that it would be non-negative, that this function will be symmetric, and that it will satisfy the triangle inequality, then all the intuition that we have for real numbers and maybe for the plane with the Euclidean geometry will transition to this abstract set. And so there's a way to vastly generalize intuitively and directly everything that we've done here to a very abstract space, and it turns out to be very convenient and very useful approach in mathematics to take those key properties and generalize them. So now that we've basically verbally defined what it means for a sequence to converge, let's see how it translates to this sequence that we've seen in the slide. So here we have plotted the elements of the sequence, and we see that farther we go with the sequence, the closer the value of the sequence become to the limit. So now suppose that I choose some positive value of epsilon here. So we have here epsilon. Let's start with epsilon equals to 1. And well, I say that the elements of the sequence can be as close to the limit as we please, provided that we go far enough. So for example, if I were to plot this threshold, so all the elements of the sequence starting from maybe this is the first and this is the second element, so this is probably element number 3. So from the third element on, all the elements with index greater than 3, their distance from the limit is smaller than 1. Okay, but I really want to show that this is the limit, so I say that it can be arbitrarily made, the distance between the elements of the sequence and the limit can be made arbitrarily small. So now let me decrease this epsilon. Okay, so I decrease it. I decrease it, decrease it, decrease it, decrease it, and we see that now some elements has fallen out from this threshold, but we see that from element number 6, right, we see that all the elements with index from 6 and on, their distance from the limit is less than 0.43, and I can make it for every epsilon. So if I were now to demand that the distance of the elements of the sequence from the limit is smaller than, say, 0.1, let's go here, then yeah, let's take it to 0.1, then I can make it happen, right? Basically, starting from, we need to treat this like an inequality that we can solve, but there exists a place here, starting from element 21, as you can see here, the distance of, from 21 or maybe a bit farther, this is above the line. So let's say, to be on the safe side, let's say that from, at least this is what we visually see, we'll later prove it rigorously, how to find this place, right, as a function of epsilon. But we see that starting from element 24 even and on, the distance of all the elements with index 24 or bigger, the distance between them and the limit is smaller than 0.1. And I can take epsilon to be as small as I please. If I make the epsilon to be even smaller, then some elements fall off again, but I can go farther enough here. If I go far enough, then again I see, okay, so if I want epsilon to be 0.44, then starting, it doesn't matter, but it works for element number 70 on, right? All the elements with index bigger than 70, their distance from the limit will be smaller than 0.044, etc. So this idea that for every epsilon, I can find this n of epsilon, this natural number, starting from which the distance of all the elements with index greater than the n of epsilon, their distance from the limit is smaller. And if I want epsilon smaller, then how far I need to go depends on epsilon, but I can make it even smaller here. So make it even smaller implies that we need to go farther with the sequence. So let's go farther with the sequence. Let's go far enough, right? Becomes more sensitive, and we see that, for example, for sure, for all the elements with index greater than 220, all the elements whose index is greater than 220, their distance from the limit is smaller than 0.014. And so it is in this sense, we will go back to the rigorous definition, that this number 0.6 is the limit because it works for every epsilon. For every epsilon, I can make it as small as I only wish. Well, 0 will not work, but I can make it even smaller like that. So here I'll really need to go very, very far, but it's doable. Let's try. Let's try and see if we go very, very far with the sequence. You see now those dots are a bit, you know, in order for us to be able to see them, they are plotted as those fat dots, but okay. But they're not supposed to be that fat. I mean, they're supposed to be tiny dots, but they're barely visible. And so let's see if we can attain it. So now epsilon is 0.001, and let's see here, is it satisfied or not? Let's see. This point is still above the line. Okay, so we need to go farther. Okay, let's go a little bit farther here. Let's go far away, far, far, far away. Let's go close to 10,000, maybe 5,000 elements. Let's go to farther here. Okay, let's go here and see if it's already good enough. Yes, so we see that for sure, if we want the distance of the elements from the limit to be smaller than 0.01, then starting from this place, all the elements with index 3010 or more, their distance from the limit will be smaller than 0.001. And this can be done for every epsilon. And this is the idea of the definition of the limit. This is the essence. So now that we have seen the visualization of the definition, let us give finally the very rigorous definition of the limit or the convergence. So we have the sequence an, and we say that this sequence an converges to the real number L, or converges to L is the limit of the sequence, if for every epsilon, right, epsilon is this accuracy threshold, we can find this natural number n of epsilon that depends, this natural number is dependent upon epsilon, such that, well, remember that we say that the distance between the elements of the sequence and the limit can be made as small as we please, provided that we go far enough. And how far we need to go to attain this threshold depends on epsilon. So for every positive epsilon, there exists a natural number n of epsilon, such that for every natural number n that is greater than this n of epsilon, provided this means that we've went far enough, the distance between the sequence and its limit will be smaller than epsilon, and we denote this by writing this familiar expression that says that the limit of an is L, or that the sequence an converges to the limit L. Now, the only thing that we really needed here to define convergence to a limit is this notion of distance. If we were to replace this absolute value of the difference by any distance function, then we could define the notion of convergence in any metric space. Now, here specifically, we need to think of this again as when we will be proving by definition that a certain number is the limit of the sequence. So a simpler way of seeing this is, because sometimes I know that this absolute value makes things more complicated for the students, is that this means that for every epsilon, two constraints are satisfied, right? This is equivalent to saying that an minus L is smaller than epsilon and bigger than minus epsilon, as we have seen with the visualization with the vertical lines. And this means basically that this system of inequalities is satisfied by infinitely many natural numbers n, and in fact, if it's satisfied, if this system of constraints constraints is satisfied by some number n 0, then it is also satisfied by any n that is greater than n 0. This is the essence. Okay, so now, for example, let us prove by definition that the limit of the sequence is 0. And so I need to show that the distance of 1 over n and between 1 over n and 0 can be made as small as we please, and provided we go far enough. So to prove this, I need to show that whenever I'm given an epsilon, I have a way of computing how far I need to go, right? Or computing this n of epsilon from epsilon. And this would be, in essence, the proof by definition. So again, what I want to show that the distance, the absolute value of 1 over n minus 0, so here we're talking about positive numbers, so this is in essence 1 over n minus 0 absolute value. So what I want to show is that this inequality can be satisfied starting from some point for every n that is big enough. Okay, so let us think of this as trying to solve this inequality and see that it is satisfiable for all natural numbers starting from some place. Okay, so now we can manipulate this inequality so these are positive numbers. So we see that right away that this inequality is equivalent to n being greater than 1 over epsilon. But of course, n is a natural number. So what we can do here is we can take the floor function, right? We can round it to the nearest natural number that to this value. But then again, we could be decreasing this, but we decrease it by at most 1. So the idea would be that we will define n of epsilon. We'll choose this to make sure that n of epsilon is integer. We will take the integer value, but in order we could have made this smaller, right? But taking the integer value cannot decrease this number by more than 1, so we add 1 to be on the safe side. And now we know that for every natural number n that is bigger than n of epsilon, we will have in particular that this n is bigger than 1 over epsilon. And if n is bigger than 1 over epsilon, this is equivalent to saying that 1 over n is smaller than epsilon. That is, we have proved that for every epsilon, there is a way we can compute n of epsilon by this formula, and then every natural number n that will be greater than this n of epsilon, we will have this constraint. We will have that 1 over n minus 0 absolute value is smaller than epsilon. Okay. Now let us see this a bit more complicated example for the sequence that we have seen in the visualization. So now I want to prove that the limit of the sequence is 0.6 or 3/5. Okay, and how could I argue intuitively that this should be the limit? Well, supposing that n is huge, like billions, right? So when n is billions or billions, right, then this is negligibly small number with this 2 and minus 1 over n. This makes it like a bit oscillate, but still it's very, very small number. And what we have here, so if n is a billion, right, then this 2 is kind of negligible. We can ignore this 2. It really doesn't contribute much. Of course, it's not a rigorous argument. I'm just giving you the intuition here. We'll see a rigorous way of doing this. And the same with this 1 over here. We have 5 billion, so we can like kind of ignore this 1. And so what we see here, so it's 3n over 5n. This n is kind of reduces, so it's 3/5 plus something small, which can be made as small as we please. And so it is reasonable, therefore, to assume that 3/5 is this limit, or at least to guess that this is this limit, and now we'll prove it rigorously. So let us remember what I need to prove. I need to prove that this expression can be made arbitrarily small, right? And I can make it smaller than any epsilon that I wish. And this inequality is actually solvable, okay? So we can demand that this is smaller than epsilon, and this inequality starting from some n for every n that is bigger than it is being satisfied. So let's see how it's done. So bringing this to a common denominator, what we have here is that we've basically made a common denominator of this and this, and this remained. Now we can use the triangle inequality, and using the triangle inequality, it's smaller than this plus that. Okay, and now we can remember, or let us just emphasize this point, that what I need to show that such n of epsilon exists, I didn't say that I have to provide you the smallest possible n of epsilon for which it is satisfied. I just need to provide some of those. And so well, now I will make some simplifications that will make it easier for me. And I'll say, well, this expression, if I remove this one, we have this, of course, something positive here. So when we make the denominator smaller, we make the whole fraction be bigger, right? And so I would say that removing this one, this is smaller than this expression, right? And then I can add those two. It's basically 2 plus 7 over 25, and all of it times 1 over n. So if I were to show you that I can make this expression smaller than epsilon, right, for every n that is big enough, then of course I can make this expression as small as I wish. So this means that for every n we have, that this is, after I add those together, so let's follow here. This is smaller than 57 over 25 over n, okay? And now if let us look at this inequality. I basically will solve this inequality, and I'll choose n such that this expression is smaller than epsilon. And then if I show it for this sequence, then it follows for this sequence as well. Okay, so this is an inequality is equivalent to n being bigger than 57 over 25 epsilon, and again we want it to be an integer number. So what we can do, we can take the integer value of this and add 1. So we have seen this trick previously. So now for every n that is bigger than n of epsilon, this means that this n is in particular bigger than 57 over 25 epsilon, which means that if we get back that n is bigger than this, and if n is bigger than this is equivalent to this being smaller than epsilon. But this expression is bigger or equal to this expression, which eventually means that this distance will be smaller than epsilon. So here is a way of computing this n of epsilon. If I want this to be smaller than epsilon, then let us compute this number, right? Computing this number in the following way, we see this n is dependent on epsilon, and we see that every n that is bigger than epsilon, this inequality will be satisfied. And this means that we have proved by definition that the limit of this expression is 3/5, because if we wish, right, we wish this expression to be smaller than epsilon, then actually I have shown you a way. If you want this to be smaller than any epsilon, you can achieve this, provided that you make this computation. And this is how far you need to go. Basically, with proving a limit by definition, it's a game. You say, if I want to prove to you that this sequence converges to a particular limit, it's a game that we can play. You say, okay, you claim that this is the limit, then can you prove to me, or can you show me that starting from some place, the distance between the elements of the sequence and the limit is smaller than 1,000? And I say, sure, this is make this computation, and here's this natural number. And beyond this natural number, all the elements in the sequence, their distance from the limit will be smaller than 1,000. And then you can say, okay, what about 1 millionth? And I say, sure. For 1 millionth, go here, make this computation, and beyond every number n that is bigger than this number, the distance between the sequence and the limit will be smaller than 1 millionth, and it can be done for every epsilon. So let us now go back to our visualization and see how it works with this n of epsilon. So now that we have defined the notion of convergence of a sequence rigorously, and we have seen how this definition works, let us now introduce some topological terminology and see maybe a simpler way of thinking about this, or an alternative way which turns out to be easily generalizable to other spaces, or more naturally generalizable. So this notion of almost all is super important in mathematics. So suppose that we have a sequence, it's an infinite sequence, and of course finitely many elements are not that interesting. We're interested only in infinitely many sequence elements, and we can take a sequence and actually ignore uh, finitely many elements of the sequence, and it will not affect the limit, as we will see. And so we say that a certain property of a sequence is satisfied by almost all the elements of the sequence, almost all, if it is satisfied by all the elements except for finitely many. So this is important. Okay, and so now let us think of distances and what it means to have a distance function. So let us now ask a question, right? Suppose that we are in this three-dimensional space. What is it a ball? So a ball of radius r is the collection of all the points in space whose distance from a fixed point, which we call a center, is smaller than some number r, which is called the radius, right? So this is a ball, and we can define a ball in any metric space, right? In any space where we can measure distances, we can define this general notion of a ball by saying, given a center point, we can now look at all the points whose distance to this point is smaller than this radius. This will be called an open ball, right? And this is super important, and we will see why in terms of convergence. Okay, so let us now make this definition. So let XD be a metric space. That is a space where we can measure distances. So a natural generalization to a ball in the space would be around centered at the point x0 with with a real number r, which we think as the radius of the ball. So we define the open ball as the set of all points whose distance from x0 is smaller than r. So of course it's a natural way of generalizing balls, and metrics can be weird, and metric spaces can be weird, and balls can be also weird on those spaces, but nevertheless some key properties are maintained in this generalization. So it's important to introduce this abstract thinking, I think, early on. Okay, and so this this ball is the open ball because we do not include all the points whose distance from x0 is exactly r. We take all those that are smaller than r, and this is called the open ball, and it will use it. It will play a role in defining what it means for a set to be open. It turns that this is our basic open set. It's our measurement to being open in a sense that we'll see. And when we take all the points with the boundary points, including the points whose distance from x0 is exactly r, this is called the closed ball. And those are two very important examples of what we call in topology or in mathematics open sets and closed sets. But okay, so and of course in our Euclidean space or in the space R3, the three-dimensional space, those are very intuitive, and they coincide with our intuition, provided that we take this Euclidean distance function, right? So that we measure the distance between 2 points in space, just with our familiar way, or with the square distances formula, right? And the square root of that. Okay, so of course, in a plane, an open ball in a plane will be the locus of all the points, and this is our distance function, right? So if we would want to generalize the notion of convergence of a sequence of points in the plane, then we would take this d to be our distance function, and the definition goes without changing. We just change the distance function. We say that in the plane, this is our d, this is our distance function, and convergence with respect to this distance, and it's the same definition for the plane, or for the three-dimensional space, or for any n-dimensional Euclidean space. And so this open ball, you see that we do not draw the boundary, so those boundary points are not included, and this is the Euclidean open ball. Okay, and if we take this closed ball with the boundary included, then this is the Euclidean closed ball, the location of all the points whose distance from this ball with radius r centered at the center point x0, y0. And so, of course, this is the collection of all points in the plane whose distance is smaller or equal than r, than this radius r. And yeah, this doesn't necessarily has to be the origin. This is the point x0, y0 here, right? Okay, and so what does it mean to have a ball in one dimension, a ball in R, right? So this is the collection of all points whose distance from x0 is smaller than R with respect to this distance function d on R. But this means that this open ball coincides with this open interval. This is exactly what it means to take all the points on the real line whose distance from x0 is smaller than R. They all lie between x0 plus R and x0 minus R. So this is our open ball on the real line. And similarly, we have the closed ball, which is this closed interval of radius R. Okay, and sometimes it is convenient to call this the R neighborhood of x0, or in particular where R is this positive epsilon, this positive number, then we would call this epsilon neighborhood. Okay, and so now let us restate and give an equivalent definition of convergence. So suppose that we have a sequence an. It could be a sequence of real numbers. Here it's understood that this is a sequence of real numbers, but it really generalizes to arbitrary spaces where we have distance on, or even just a topology, but let us ignore topology for now. Then we say that the limit of an is L if every epsilon neighborhood, so epsilon neighborhood is this ball with radius epsilon centered at L. So every ball centered at L, I mean all the points that whose distance from L is smaller than epsilon, contains almost all the elements of the sequence. Okay, it contains all the elements except maybe for finitely many. And so now when we give two definitions to the same thing, let us show that these two definitions are equivalent. So this is in fact a theorem. So the definitions for the limit of the sequence that were given here are equivalent. And let's prove it. So suppose that we have sequence an that converges in the sense of the first definition. So this means that for every positive epsilon, there exists n of epsilon, such that for every n that is greater than n of epsilon, an minus L is smaller than epsilon. This is the original definition. But this inequality is equivalent to saying that an is between L minus epsilon and L plus epsilon, which is equivalent to saying that an is lying in this interval. But this, oh, sorry, it has to be plus here. It's a typo here. I will fix it. So between L minus epsilon and L plus epsilon. And therefore, this is the epsilon neighborhood of an, right? But this epsilon neighborhood contains all the elements of the sequence except maybe for the finite collection a1 up to an. So those elements a1 up to an, they may not satisfy this inequality, but there are finitely many of them, and therefore they may not lie in this epsilon neighborhood. All elements starting from n of epsilon plus 1 and on has to satisfy this inequality, and therefore has to lie in this epsilon neighborhood. And so this epsilon neighborhood contains almost all. So it has to contain all the elements of the sequence except maybe for those, right? So this epsilon neighborhood contains almost all the elements of the sequence except maybe for finitely many. And since epsilon is arbitrary, this means that every epsilon neighborhood contains almost all elements of the sequence. This is how strong this definition means. And yeah, this is what I have said. So if the sequence converges according to the first definition, it also converges according to the second definition. Now suppose that it converges according to the second definition, right? We need to show that it converges according to the first one. So this means that let us pick an epsilon, right? And let us now pick an epsilon neighborhood of L. And so the second definition says that every epsilon neighborhood of L contains all the elements except for finitely many elements. So now let us define this set A, which will be the set of all the natural numbers within the natural indices, such that a k lies outside of this interval. Now, since an converges according to this definition, this set is finite. And as a result, every finite set has a maximal element. Now, the maximal element of this set A may depend, of course, on epsilon. So let us call the maximum element of A, let us denote this by n of epsilon. And this is it. Only elements of the sequence whose indices are in A may lie outside this epsilon neighborhood. All other elements, in particular for every n that is greater than this, they must lie inside this epsilon neighborhood, right? And so this means that for every epsilon, there exists a natural number n of epsilon, which I said how to define. It's just the maximum of this finite set. And then every n that is greater than n of epsilon, for this we must have that the n lies in this epsilon neighborhood, which means that this is actually equivalent to the distance of an minus L being smaller than epsilon, that this inequality is satisfied. So we have proved that. So this is truly equivalent. So now we can generalize this quite naturally to convergence in arbitrary metric spaces where the only thing that we have is a way of measuring distances. And this space can be very, very abstract. And even this condition can be relaxed on having a metric. It's just what we essentially need is the notion of neighborhood or an open neighborhood, as we will see, to define convergence. And this is something very strong. This is a vast generalization, and I'll tell you why generalization is important, because when you generalize something, on the one hand, it's more abstract and harder to work with. On the other hand, once you prove a theorem for something abstract, you have proved a multitude of theorems, a lot of theorems for many, many, many cases, right? And this is the power of mathematics, is actually this generalization and abstraction. And so it's important, to early on introduce this, on the one hand, abstraction, and on the other hand, to show its connection to concrete cases. So now let us define the convergence in a metric space. So let xd be a metric space, and let an be a sequence in X, right? And so we say that this sequence an converges to some point x0, which is an element of X, and we write this in the same way. X can be a very abstract space. If for every epsilon we can find a natural number such that for all n that is greater than n of epsilon, the distance between an and x0 is smaller than epsilon. And equivalently, this means, right, that for every epsilon there exists n of epsilon such that for all n that are greater than n of epsilon, we have that an lies in the epsilon neighborhood of x0. And so this general notion of saying that a sequence converges to a point x0 in limits in a metric space. So to say that an converges to a point x0 in a metric space is the same as saying that every epsilon neighborhood of this point or open ball around x0 with a radius epsilon contains almost all the elements of the sequence. That means all except for maybe finitely many. Okay, and so let us now study this important set, the open sets, those super important sets of open balls, because we have seen that with those we can define the notion of convergence, right? And all we need to define those is a metric. And we'll see that there are other generalization. So those open sets can be even defined without the notion of distance, but all in its right time. So for now, suppose that we're still in R, right? And so let's see what are the key properties of those open balls in R, but in fact they hold for any metric space. So what we see here is that for every point x in this open ball, which is in fact just an open interval, we can find an even smaller open ball that is centered at x and is contained in this original ball. That is, so if we say this is radius delta, then the ball around x with radius delta is contained in this ball. So let us first prove this. So the idea, of course, if we were to visualize this, is that this open is interval, and so x never reaches the boundary. If we had this closed interval, right, and we take the edge point, then every neighborhood of this point x will contain elements inside the interval and outside the interval, right? Every neighborhood. But since this interval is open, then there is, for every point that we choose, it has positive distance to the edge, right? And then we can take a neighborhood with radius that is smaller than the distance to the edge. So let us see how do we do it. Suppose that x lies in this ball of radius r around x0. That means that basically this is the open interval x0 plus r and x0 minus r. And so this is equivalent to saying this. And so what I wanted to show that then I can find a ball around x0 such that for all points in the ball around x0 the distance is going to be smaller than r. So it's easier to understand when it's just written. Okay, so suppose that x minus x0 is smaller than r. This means that there exists some positive h, right, such that this is a typo, sorry. H is greater than 0. That's the only thing that I meant for this to be. So let us denote x minus x0. We have this positive h. So let us denote this by r minus h, right? Because x minus x0 is strictly smaller than r, then we can define h by r minus this. Okay. And let us choose this delta to be h half of this distance. Then let's see what we have. Then for every y in this interval of length delta around x, let's see what we have. So first of all, if the distance from y to x is smaller than delta, and delta is h half, right? And in addition, we also have that the distance between x and x0 is r minus h, right? So now let's see if we use the triangle inequality. This is the importance of the triangle inequality to show this property of open balls. Okay. So now suppose that y is any point whose distance from x is no more than delta, right? So we take any such y. And now what we do here, we use the triangle inequality here. We could add we could subtract x here and add x here. And so using the triangle inequality, we see that this is no more than that. But the distance from y to x is smaller or equal to h half. And this distance is r minus h. And so what we have here is r minus h half, and h is positive, so of course it is smaller than r. So what we have proved is that for every point whose distance from this x is smaller than delta, which is h half, its distance from x0 is still going to be smaller than r. And this means that this ball of radius delta around x, or an open interval with radius delta around x, is contained in this ball of radius r around x0. And this is the way to visualize this. So maybe it will be easier to see. So this is x0. So here I took a two-dimensional ball, but we can think of it also as just this interval. So this is the center point x0, okay? And this boundary is not included. These boundary points are not included here. So for any x here, right, I can look at this distance is actually from x to the edge to this. This distance is r, is positive. So I can find an even smaller ball around x0 that is entirely contained in this open ball. And I can do it for every point in this open ball. And if the ball was closed, suppose that there's a boundary point over here, then for boundary point it will not work, because for a boundary point any neighborhood will contain points from outside and from inside the set. But since those boundary points are not included, I'm always on a safe distance from the boundary, even if I'm here. So I can always find a ball that is small enough that will still be contained entirely in this open ball. Okay. So this inequality, or this property of open balls, shows that open balls are open sense in a way that we will define. So we have seen that for every x in the open ball, we can find an even smaller open ball that will be contained in the origin ball. This is the key property of open sets in metric spaces, and in fact of open sets in general. So restating this, if we say it in the natural language, around any point in an open ball, we can find an open ball that contains this point and is entirely contained in the original ball. So, and of course, to prove this, the key property that we used of the distance function was the triangle inequality. Okay, and this property of open balls is that important, so it's valid also in any metric space. So now let us just, this can be proved in an arbitrary metric space. So let XD be a metric space. We have used the distance function. So if we get back here, we use this distance function and we used this specific properties of the absolute value. But what we really needed is this triangle inequality. So we can now take this property and show that it is valid in any metric space, and this proof goes unchanged except for changing this absolute value of the distance by a distance function. Okay, so let's see how it works. So the theorem is goes as follows. So for any metric space and any point and r a real positive number, then for every x in this open ball, there exists a positive number delta greater than 0, such that the open ball with radius delta around x is contained in the open ball around with radius r around x0. Sorry, another typo here. So an open set U in a metric space will be defined as, so now if we want to generalize this desired property of open balls, so we will say that a set is open if around each point in the set we can find an open ball which is entirely contained in this set. So an open set U in a metric space will be defined as a set such that I've already said that for each point x in U we can find a positive delta such that the ball with radius delta around any point in the set is entirely contained in U. So for every x there exists a positive delta such that the ball with radius delta is contained in the set. So now if we define open sets in such a way, so a set is said to be open if around each point in the set we can find an open ball that is entirely contained in the set. So using this terminology, we have proved, this theorem says that open balls are open sets, right? Often happens in mathematics. So, and let's see, as I've mentioned, the previous proof remains unchanged except for changing the metric, right? So indeed, suppose that we take, here we don't have a typo, any point in the ball with radius r around x0. This means that for this point, the distance between x and x0 is smaller than r, okay? And let us choose h to be the distance, the difference between r and this, and of course, by definition, since this distance is smaller than r, then r minus this is some positive number h, okay? And now let us choose delta to be h half. So now for every point in this ball with radius delta around x, any y that lies in this ball satisfies that the distance of y from x is smaller than delta, which we have chosen as h half. So this h is actually the distance to the boundary, if, so to say, okay? And the distance of x from x0 is r minus h, and now we add those two and use the triangle inequality for the metric. And so when we add those two, this is what we get. So on the one hand, this is h over 2 plus r minus h, which is r minus h half. H is a positive number, so this is strictly smaller than r. And on the other hand, using the triangle inequality, we see that this has to be greater than the distance of y from x0. So in fact, what we have taken, we have shown that arbitrary point, any point y in a ball with radius delta around x, right, any point, the distance of y from x0 is smaller than r, which means that y lies in this ball of radius r around x0. Okay, so this is, the last sentence is just what I said verbal. Okay, so again, the definition of open sets in a metric space. So let xd be a metric space, a subset u of x is said to be open if for every point x in u we can find positive epsilon. Doesn't matter, it was delta previously, but we can find a positive number such that ball with this radius epsilon is entirely contained in this set U. Okay, and so we have seen that there is an actual way to define open balls in metric spaces and open sets in metric spaces. And in the essence of topology is defining what are open sets and their key properties, and more about this will be in a course in topology. But it is really important to introduce those concepts together. So now when we have a metric space xd and any point x and x, so we would say that, we want to define the notion of a neighborhood. So we say that a set W is a neighborhood of X if this W contains an open set that contains X. This is what it means to be really a neighborhood. And this is the only important thing. So again, an open set is a set such that for every point in the set we can find a ball with small enough radius that is entirely contained in a set, and this is an open set. And now for a neighborhood of a point x is something that is some set that contains an open set. Okay. So now using this terminology we can really give a general definition of convergence, and basically what we would say is that a sequence converges in a metric space or even in a topological space if every neighborhood of this limit, so a sequence converges to a limit L, if every neighborhood of the limit contains almost all the elements of the sequence, right? So this is the definition. So a sequence again in a metric space X is said to be convergent to a limit point x0 if every neighborhood of x0 contains almost all elements of X. And so proposition, so the current definition is equivalent to the previous definitions, at least in the case of for metric spaces. And so let us make this observation. So changing any finite amount of elements of a sequence, as we've said, will have no effect on the convergence of the sequence or on its limit. So a convergence is really a property of the infinite. It depends only on the tail, on the infinite tail of the sequence, and not on its head, or not on its initial starting elements. It's an emerging property of infinity, so to say, like convergence. Okay, so now let us prove that those definitions are indeed equivalent. So again, for every epsilon that is greater than 0, the open ball with radius epsilon around x0 is an open neighborhood of x0, is in particular neighborhood, because a neighborhood is something that contains an open set, and an open set is something that contains an open ball. Okay, and this means that according to this definition, that all but finitely many elements, it's the same proof that we have previously, of the sequence lie in this ball of radius epsilon around x0. But this means, so if, again, as in the proof that we have seen, if n of epsilon is the maximal index of those finite numbers that lie outside of this ball, right, then all the elements with index greater than n of epsilon must lie inside this ball. But this means that for every n that is greater than n of epsilon, that they lie inside this ball, which means that their distance from x0 is smaller than epsilon. And so we see, again, we have proved that convergence according to this definition implies the convergence according to the previous definition, right? So we have proved that this definition implies the ordinary convergence in metric spaces. So this means that a n converges to x0. And now conversely, suppose that this sequence converges to x0 according to the old definition, then it means that in every neighborhood we can find a ball of radius epsilon around x0, of course, right? Because a neighborhood is something that contains an open set that contains x0, but an open set necessarily contains this open ball of some radius, right? And this means that, sorry, so for every epsilon, this means that there exists n of epsilon such that for every n that is greater than n of epsilon, a n is in this ball. And so, again, this indicates that only finitely many elements can lie, because for every n of greater than n of epsilon, all the elements lie in this ball. This means that only elements from 1 with indices from 1 up to n of epsilon may lie outside this ball, right? And all others must lie inside this ball. So if we were to visualize this, for example, for a sequence of points in the plane, where we have a way of measuring distance, right? Then, and we were to draw this ball of radius epsilon, then similarly to what we have seen in the visualization, only finitely many elements will lie outside of this ball, and the rest will be inside. And this can be done for any epsilon. I can take this epsilon as small as I please, and again, only finitely many elements of the sequence will be outside of this ball, and the others will be inside. Okay, so let us see more examples, or let us see what it means for a sequence to be not convergent, according to definition, right? So a sequence does not converge to the limit x 0, right? Again, so let us make the logical negation of that definition. So in the definition we had for every epsilon, now the negation would be that there exists epsilon 0, such that for every natural n, we can find index that is greater than this n, such that the distance between the elements of the sequence and the limit candidate, which is not the limit, is greater than epsilon 0. And in other words, it would say that it's easier to think of this in terms of the second equivalent definition, that for every epsilon neighborhood of the limit, there will be infinitely many elements that are lying outside of this neighborhood, right? So again, so we could say that the sequence does not converge if there exists a neighborhood of x0s, any neighborhood. It's enough to have any neighborhood of x0 such that infinitely many points of the sequence lie outside this neighborhood. So why we say that there exists a neighborhood? Because suppose that we take a giant neighborhood, then it could happen that this very big neighborhood, this very big set that contains an open set, it could happen that it contains by accident all the elements of the sequence, right? But this will not work for every neighborhood. There would be some small enough neighborhood that will miss an infinitely many, or that will fail to contain infinitely many elements of the sequence. This is the meaning of that. Yeah. So restating it, if we look at neighborhoods around a ball, for example, with radius epsilon 0, so there would be infinitely many points lying outside this ball, right? So, for example, let us go to the sequence that we've seen at the beginning, an, which is minus 1 to the power of n. This sequence does not converge to any limit, and let us prove it, right? So first, let us show that it does not converge neither to 1 or to minus 1. Of course, and okay, so an doesn't converge to 1, since we can choose, for example, epsilon 0 to be 1, right? And then all the collection of all the points whose distance from 1 is smaller than 1, it is this interval from 0 to 2, right? And so all the elements of the sequence with odd index, they will be equal to minus 1, and they're lying outside of this interval. So epsilon 0 can be chosen here as 1, and then if we choose epsilon 0 to be 1, then infinitely many elements, right, of the sequence will lie outside this interval, right? And similarly, we can do the same for minus 1, right? So in the sense of the definition, for every number that you choose as big, you can choose a number as big as you please. You can always find an index that is bigger than this number, whose distance from such that the element with this index, its distance from 1 will be greater, for example, than this 1. And similarly, it's with minus 1, right? So because here we have this sequence from 0 to 2, this interval of 0 to 2, this open neighborhood of 1 from 0 to 2, fails to contain infinitely many elements of the sequence, right? Okay, and so similarly, the sequence does not converge to -1. So let us show that it cannot also converge to any other value, okay? And so if a is not 1 or -1, let us denote epsilon 0 to be the minimum of a minus 1, or if a is this limit, right? If a is any number. So let us consider a minus 1 and a minus minus 1, which is actually a plus 1 in absolute value, right? So this is the distance of a to 1, and this is the distance between a and minus 1. And so if a is neither of those, then this is going to be some positive number, okay? But then choosing this epsilon 0 implies that for every n we have for this particular sequence, because it's either 1 or -1. So, of course, choosing epsilon 0 like this, we see that for every n, we will have that the distance of a n from n is greater than epsilon 0, and therefore the sequence does not converge.